Welcome to today's Explainer, designed specifically for elementary science educators. We're jumping right into Competency 008A, mastering the physical and chemical properties of substances. But we're not just going to talk theory here. We're really going to focus on mastering measurement. We want to give you the procedural confidence to teach tools like the triple beam balance and the graduated cylinder, without the usual classroom chaos. We'll break down exactly what you need to know to build this crucial scientific foundation.
Here's our roadmap for this explainer. First, we'll look at the shift from description to measurement. Then, we'll distinguish mass and weight, establish the density benchmark, contrast conduction with resistance, and wrap up with the Mohs hardness scale. All right, Section 1, from description to measurement. Let's look at the primary pedagogical shift required by Competency 008A. The critical leap we need our students to make is moving away from just qualitative identification, merely describing how a substance looks or feels. We want to push them toward quantitative verification, where they extract exact, measurable traits. It's the difference between a kid saying, hey, this rock is long, and confidently stating, this rock is exactly 14 centimeters long. And a lot of that starts with something as simple as the standard metric ruler. Now, here's a crucial pro tip to highlight for your classroom, the absolute most common student error: starting their measurement at the physical plastic edge of the ruler instead of the actual zero mark. You literally have to explicitly teach them to align the object with that zero line for exact quantitative verification. So, physical and chemical properties cover a really wide range of characteristics. We're talking size, shape, temperature, magnetism, hardness, mass, conduction, and density. It's super easy for an 8-year-old to tell you a magnet sticks to the fridge, right? Or that a piece of metal just feels cold. But your ultimate goal as an educator isn't just getting them to memorize definitions or make passing observations. It's to guide them to verify these exact properties through structured, hands-on scientific measurement. We want them finding the exact numbers behind the concepts. Moving right along to Section 2, distinguishing mass and weight. Let's clear up one of the absolute most common points of confusion you'll run into in elementary science. The crucial point here is establishing this dichotomy for your students from day one. They have to understand that mass is the universal measure of the amount of matter an object contains. Think about it. If you take an apple, or say an astronaut, all the way to the moon, their mass is identical to what it is on Earth. It never, ever changes based on location. Weight, on the other hand, fluctuates entirely depending on a system's gravitational pull. Because the moon has way less gravity, our astronaut weighs less, even though their mass remains exactly the same. It's a foundational distinction they just have to grasp before they can accurately measure either one. And to find that true universal measure of mass, you obviously can't rely on simple observation or guessing how heavy something feels in your hand. You've got to teach your students to use precise, dedicated tools like the triple beam balance. Procedurally, this means teaching them patience. You'll show them how to move the riders one at a time, starting with the largest 100-gram increment, then moving to the tens, and finally the ones, until that pointer aligns perfectly with the zero mark. Which brings us to another massive pro tip. The most common error in the lab is failing to zero out or calibrate the balance before placing the object on the pan. Always remind them to check that the empty balance points to exactly zero first. Otherwise, all their hard-earned data will be completely skewed. Next up, Section 3, the density benchmark. Let's examine a foundational physical constant that helps students predict how objects interact with their environment. Density is calculated by taking mass and dividing it by volume. Now, as a teacher, you know mass comes from your balance, but finding volume often requires a graduated cylinder. And when teaching the graduated cylinder, procedure is literally everything. You must instruct students to place the cylinder on a flat surface and physically lower their body down to read the water level. So here's your pro tip. The classic rookie mistake is reading the top edges of the water that kind of cling to the glass. You have to train them to read the meniscus. That's the lowest point of the curved liquid at strict eye level. Once they have that exact volume and they divide their mass by it, this calculation unlocks a whole new level of physical science. It tells us exactly how tightly packed the matter is within a given space. And to put that into perspective, the benchmark density of water is exactly 1.0 grams per cubic centimeter. Why is this specific number so vital? Well, because this is the exact number your students will use to predict whether an object is going to sink or float. If they measure a mystery object, do the math, and calculate its density at 1.2, they can confidently predict it'll sink before it ever even touches the water. If it's less than 1.0, they know for sure it's going to float. You're giving them predictive power based on actual math, which is just an incredibly exciting light bulb moment for young learners. Okay, Section 4, conduction versus resistance. Let's see how physical traits determine energy flow. you've got to guide your students through a really critical contrast here, differentiating between conductivity and insulation. Conductivity is the property of matter that allows energy to flow easily, right? So you'll teach them about electrical and thermal conductors like metals. In total contrast, we have insulators, which block energy transfer. And this is where materials like rubber or wood come into play. A great way to explain this is to ask your students why cooking pots are made of metal, but the handles are wrapped in rubber or plastic. It's the perfect, relatable, real-world entry point to explain how we harness and control energy, keeping the heat where we want it and protecting our hands where we don't. And finally, Section 5, the Mohs Hardness Scale. We're looking at how matter is classified by relative tests. Frameworks like the Mohs Hardness Scale are just incredibly useful in the classroom because they perfectly capture the extreme spectrum of mineral hardness. They give students a comparative baseline. We obviously don't always have a fancy digital machine to measure exactly how hard a rock is, so we have to compare materials against each other. Down at a level 1, you have extremely soft minerals like talc, which you can literally scratch with your fingernail. And all the way up at a level 10, you have diamond, the hardest natural substance. It's just a really elegant way to organize properties that we test relative to one another. But the real magic happens when you put this into practice. Students will use this exact scale in the classroom, physically applying scratch testing to identify the unique traits of mystery mineral specimens. If a student takes a piece of quartz and successfully scratches a piece of fluorite, they've just actively proven that quartz sits higher on the scale. They're testing which minerals can scratch others to figure out their relative place, basically turning a static table of data into a totally dynamic, hands-on investigation. Honestly, it feels like detective work, which is absolutely the best way to learn science. We have covered an incredible amount of ground today, moving from simple descriptions to exact quantitative measurements involving mass, density, conduction, and hardness. As you prepare your lessons around Competency 008A, I want to leave you with this final thought. How will you guide your students to discover the exact traits of their next mystery substance? Will you let them just guess and eyeball the edges of a ruler? Or will you teach them to read the meniscus, zero out that balance, and truly measure the world? Thanks for joining me for this explainer.